On today's episode, we are going to upgrade our printer to be able to print high temperature filaments such as ABS, Nylon, PETG, and TPU, all by replacing this small part called a heat break. First, we'll discuss why we want to replace it, then we'll see how to replace it, and finally, we'll see some prints after we've replaced it. And here we go. Folks, welcome to the channel. I am Leo of Prince Leo 3D. If you're a subscriber, welcome back. Now, people always ask if the Voxelab Aquila can print certain materials, namely ABS, TPU, Nylon, and PETG. The answer to that question is yes. Our stock Aquila comes completely capable of printing those materials. The real question is, should we print those materials with the stock Voxelab Aquila? The answer to that is no. To understand why, we need to take a closer look at our Aquila. Now, the Voxelab Aquila is what's known as a Bowden style 3D printer. What that means is the cold end of the extruder has been separated from the hot end of the extruder. And what connects the two is this very long tube called a Bowden tube. Now, that term, Bowden tube, is not unique to 3D printing. It's actually a mechanical term. And for us, it's necessary to maintain the filament path from the cold end all the way to the hot end. Now, you may have also heard myself or others refer to this tube as a PTFE tube. That would be its material name. PTFE, short for polytetrafluoroethylene, is a fluoropolymer, meaning it's a very high performance, very slippery plastic. And for our application, it's perfect. Now, in most applications, PTFE is non-toxic. However, when heated to very high temperatures, like those we see while 3D printing, it can off-gas harmful neurotoxins. Now, the temperature varies slightly depending on the source, but the generally agreed upon danger zone is 230 degrees Celsius and above. That means all those high temperature filaments, ABS, TPU, PETG, Nylon, that print at or above 230 degrees are possibly off-gassing harmful toxins. Now, you may think, oh, well, the Bowden tube starts here and it terminates right at the top of the hot end. And therein lies the problem. The stock hot end on the Voxelab Aquila allows the PTFE tube to go all the way through it and touch the back of the nozzle. That means whatever temperature the nozzle gets, the PTFE tubing also gets. Now, aside from the health complication, there's also print quality considerations we have to worry about. The PTFE tubing that's touching the nozzle is constantly being heated, and over time it can burn and char. This can lead to worsening print quality and possible failures. Now, we could fix this issue by replacing the entire hot end, but what if I told you there was a cheaper, simpler solution? And that is where our heat break steps in. Now, to understand how the heat break is going to help us, let's take a closer look at the parts that make up our hot end. Now, this first image we're seeing is an exploded diagram of our hot end, which is known as an MK8 hot end, and these are all the pieces that make it up. Starting from the bottom, we have the nozzle where filament is extruded. The nozzle is screwed into the heat block. This is an aluminum block that is meant to be heated so it can transfer that heat to the nozzle and melt filament. Within the heating block is also the heating cartridge. This turns electrical energy into heat, which radiates through the heating block. This is solely responsible for heating up that heating block. And then next to the heating cartridge, we have the thermistor, which detects the temperature of the heating block and sends that information to the printer's mainboard. Now, this lower portion of the hot end is referred to as the melt zone or the hot zone. Now, in a perfect 3D printing world, the heat produced here in the melt zone would stay there. However, all parts of this hot end are metal, and that heat will travel. Now, when that heat travels into the upper chambers of the hot end, it is not ideal, and it is known as heat creep. Now, when that happens, filament can prematurely soften and that can either clog or cause extrusion issues. Now, because we don't want any heat in these upper chambers, we label this, or we refer to this upper area as the cold zone. Now, the first line of defense against that heat rising into the cold zone is the heat break. The lower part of the heat break is screwed into the heating block, and then it extends upward into the cold zone. Now, this part is quite literally meant to break the flow of heat between the hot and the cold zones. The upper portion of the heat break is covered by what's known as a heat sink. The heat sink is what you see when you first look at the hot end. It is that upper finned portion. And the purpose of this heat sink is to take any of that remaining heat that's within the upper parts of the heat break and dissipate them outwards. So it's trying to pull the heat from the heat break and spread it to the outside world or the outside air, cooling it off. The flaw with our heat break is its bore, or inner diameter, is so wide that it allows the PTFE tubing to run all the way through it and touch the nozzle, thus putting the PTFE tubing in the melt zone and subject to those dangerous temperatures. Now, both of the heat breaks we replaced today are going to eliminate this problem. They only allow the PTFE tube to be inserted mere millimeters, keeping the PTFE tubing well within the cold zone. Additionally, they're both made of titanium, which is a less conductive metal than our stock stainless steel. So they should have a higher resistance to the transfer of heat, helping the cold zone stay cold. Now, we have one that is completely made of titanium, while the other is a bimetal heat break, meaning it's composed of two metals. It has the threads and internals made of titanium, while the top portion is made of copper. Where titanium has a low thermal conductivity, copper has a relatively high thermal conductivity, which means it's going to pull the heat out of that titanium core and spread it to the heat sink to be properly dissipated. So now we understand why we want to replace this heat break. Let's see how we replace this heat break. And I promise, if you replace the nozzle on your 3D printer, you're about 50% of the way there. It's not that hard. Let's see how it's done. So the first thing we want to do is begin to heat our printer. I preheat it to 220 degrees Celsius, which is lower than our danger temperature zones. This is going to heat up the filament, and it's going to help us remove the nozzle. Now, while our printer is getting up to temperature, I'm going to start removing the fan shroud. Now, the first thing you're going to notice right away is this is not a Voxelab Aquila I'm working on. This is actually a Creality Ender 3 Pro. The footage I filmed for the Aquila is lost to the ether right now, unfortunately, so I just re-recorded it on the Ender 3. However, do not worry. There is no difference whatsoever in this installation and removal process. The only difference is the fan shroud that you're seeing right now. The Voxelab Aquila, of course, has a single screw holding that fan shroud on, and it is in the upper back portion. Once the fan shroud is removed, be very careful with it. Just tuck it away, maybe along the x-axis gantry. Let it sit there. We don't want to do too much jostling with that. After the fan shroud is removed, everything should be preheated. At this point, you can try and remove your PTFE tubing if you want. Oftentimes, with these hot ends, the PTFE tube will not remove. If you want to try, you're going to remove that blue collet. You're going to push down on the silver plunger or the gray plunger on top. Push your PTFE tubing in slightly and then try and remove it by pulling it out. If it doesn't move, if it doesn't budge, don't worry. Mine didn't. I'm going to show you how I ultimately removed it. Now, having been preheated, we're going to start by removing the filament from our machine. And then we're going to go ahead and start loosening that nozzle. Now, very important step. Before we touch the hot nozzle with our crescent wrench, with our socket wrench, with anything, we want to power our machine down. If we start trying to manipulate this hot end while it is powered on and we accidentally touch the wires going to the thermistor, we could short it out. Now, once you loosen the nozzle, you could wait for it to completely cool down if you want. If not, you can remove it right away, but you have to consider this is a 220 C or somewhere abouts degree nozzle that you're about to remove. It's going to be sitting in your socket wrench or sitting at the bottom of your print bed at some point, so just be really careful. Don't burn yourself. If you want, you can even use gloves that are protected against high thermal ranges. After the nozzle is removed, this is when I unscrew the grub screw that holds in our heatsink. That's going to loosen the heat break from the behind the heatsink. Now, when you do this, you want to make sure not to completely remove that grub screw because it is very small. If it falls, it's going to be hard to find. Now, after we remove the grub screw, or we loosen rather the grub screw from the heatsink, we're going to take this hot end off the machine. At this point, we're going to want to make sure that the hot end is fully cooled because it is going to come off the gantry. It's going to have to rest somewhere. You don't want to rest it on your print bed at 200 plus degrees C, or you don't want to touch it with your hand. So getting this hot end off is relatively simple. It's 2 screws, both in the heatsink in the upper portion, one on the left side and then one on the right side. After those screws are removed, we can gently remove the hot end from the gantry. After the hot end is removed from the X-axis gantry, we can flip it upside down and we can start removing those 2 stabilizer screws that run through the heat block into the heatsink. Now, these shouldn't be too hard to take out as they should not have been muscled in there to begin with, so these should come out relatively easy. And now we can remove the heatsink from off of the heat break. We already loosened that grub screw, so that shouldn't be a problem. And we can just pull it up and off of the heat break. And now is the point where we're going to finally remove this PTFE tubing. The first thing we're going to do is power our machine on and preheat it to 220 degrees C. We need it to be hot while we do this. Now you'll notice I have my crescent wrench on our heating block while it's powered on. The reason I'm doing it now is because I have access to the opposite side of the heating block. I'm nowhere near touching the thermistor wires or the heating cartridge, so I can safely work on it. So what I'm doing is using a pair of needle nose pliers, and I'm just gently tugging on the PTFE tubing now that it's been softened at the 220 degrees Celsius temperature, and it eventually gets removed. Now, while the heating block is still hot, I take the opportunity and I begin unscrewing the heat break. I'm again using these needle nose pliers. I'm going over the top, applying a little bit of pressure, and I'm just turning this about 1/4 of a turn each time, and I'm slowly removing this heat break. Best to do it while it's hot. And then after that, because our PTFE tubing was so gnarly and had so much extra oozed filament on it, I have to clip it with a pair of PTFE tube clippers in order to remove the heatsink off it because there was just too much grizzle on it. And after that, we can remove the heatsink, and that's it for the removal. After this, it's turnaround time. We're just going to reinstall everything with our new heat break. What I'm trying to demonstrate in this next shot here is our ideal positioning. We want the threads of the nozzle to be butted up right against to the threads of the heat break. That is how we always want to tighten our nozzle. If there is any space there, molten filament will ooze between it. You'll get extrusion issues. So whenever we tighten our nozzle, there should always be some gap between the bottom of the nozzle and the actual heating block. That means it's tightening itself against the heat break and not the heat block. Now this next part is the one thing that differs between our 2 heat breaks. On our all titanium heat break, there is a small ledge above the threads. That means we should be screwing this heat break into the heating block all the way down to that shelf. Our bimetal heat break does not have that. So in order to tighten that down, the first thing we need to do is first install our nozzle by hand. We install it all the way up to the heating block, completely touching it. Then we remove it, or we unscrew it about 1 full turn to give it a little bit of gap there. And then we install our bimetal heat break until I can't screw it in anymore. That means it's touching the nozzle. So now, when we go to heat tighten this later, So we still have some room for the nozzle to tighten up and snug up even more against that heat break. That is the one difference between these two heat breaks. We're going to watch me do the titanium one, and if you all have the bimetal one, that is how you're going to do it. The nozzle is going to be inserted first, then you're going to tighten down the heat break to the nozzle, and then later you'll heat tighten it just like that. Now I start with the titanium heat break by hand tightening into the top of the heating block, and I am hand tightening it in all the way. After that, I do the same thing with the nozzle. I hand tighten it all the way into the bottom of the heating block. Now there should be a gap present because the nozzle should be touching the threads of the heat break, and it should not be sitting right up against that heating block. It's time to heat tighten the nozzle and the heat break. The first thing we're going to do is heat our machine to a very high temperature. I did 253 Celsius. We then take a crescent wrench or another adjustable wrench, hold that hot heating block in the wrench, be very careful. Then I use a 7mm spanner to tighten up the heat break, and I use a 6mm socket to tighten up the nozzle. It's a brass nozzle, be very careful, it can break very easily. Snug it up while it's hot, but don't over muscle it. After that, if you have thermal paste, now would be the time to coat the top of your heat break in it, because we are going to reinstall the heatsink right over that. We're then going to tighten up that grub screw, make sure it's good and tight so that heatsink is not going anywhere. And then after that, we are putting in the stabilizer screws. We are almost done. This is the latter half of the installation. We can almost see the runway now. So just put in those stabilizer screws. Don't over tighten them. They're just meant to be in there to hold that heating block in place. Now don't forget the silicone sock around the heating block, and then it is time to reinstall our hot end. The two screws that came out of the heatsink go back to the heatsink, and they secure our hot end onto the X-axis gantry. After they are good and tight, just do a wiggle test. Make sure there is no movement or play in that hot end. That should be completely stable. And if you had to clip your PTFE tubing like I did because it would not come out of the heat break, double check that it is cut flush. If you need to, take another snip at it with the PTFE tubing cutter to make sure that end of that tube is nice and straight. After that, we re-secure our fan shroud. Again, this is an Ender 3 Pro, so it looks a little different. I have two screws in the front, whereas our Voxelab Aquila has either a single screw in the back upper portion, or it might have two screws if you have an updated fan shroud like I do. I have the Satsana fan shroud, and that has one in the upper back and one to the front left. After that is re-secured, we are done. Congratulations. We have to do a few follow-up things. There's going to be some calibrations, of course. The first thing we're going to do after we're finished is re-level our bed. And then another huge one is adjusting our Z offset. So very important to getting very good first layers and thus very good prints. I have a video on this. I'm going to link it somewhere up above. After that, we now have what is called an all-metal hot end. Let's take a look at our initial hot end. Now you'll notice all those parts are metal, but it's not considered all metal. The reason behind that is the term all metal only means is the PTFE tubing in the melt zone. Our stock hot end had the PTFE tubing in the melt zone, so it wasn't all metal, even though the components were metal. But now with this updated heat break, our PTFE tube is outside of the melt zone, and we now have an quote-unquote all-metal hot end. That means one other thing. We're going to have to readjust our retraction. Where the normal MK8 stock hot end has a average of 5 to 6.5 millimeter retraction distance, our all-metal hot end should start around 3 millimeters, and then we can adjust it accordingly. The first heat break I tried was the all-titanium heat break we saw during the installation. After leveling my bed and adjusting the Z offset, the first thing I did was find out my new retraction settings. From there, I loaded up some high temperature filament. For this machine, it was PETG. I performed some small calibration style prints like flow and dimensional accuracy, and then once I was comfortable the material was printing properly and sticking to the bed, it was time to try something larger. This is an awesome model and it prints completely support free. It came out really nice, even though I could have probably taken some more time to really dial the temperature settings in. Overall, however, this heat break has been performing really well for me with no issues. Next is the bimetal heat break, and this is printing on my Uri 1 ER20. But again, this was installed onto an MK8 hot end, so nothing is different. It's still the same hot end the Aquila uses. Now, actually getting the MK8 onto the ER20 was a bit of a task. It required a new fan shroud, some alterations, some calibration, but it's worth it. Now, if you have an Uri 1 ER20 and are interested in completely overhauling your hot end, which I would recommend, leave a comment, let me know, and I'll look into making a video on the process I took to get here. For this heat break, I chose ABS as the high temperature material of choice. After some calibration prints, I decided to print a temperature tower, as I hadn't printed with this filament before. Now on a temperature tower, the temperatures change each section, so you can look and see where your filament is printing at its best. Now I settled on a temperature somewhere between 230 and 235 Celsius as ideal, but I actually chose to stay on the hotter side for this next model as it's pre-supported and the extra melting helps bond those pre-supported sections. This model, I have to say, is really cool and it printed so well. This is a fully articulated model, which means the arms and legs rotate freely, and after it was off the build plate, I had no problems whatsoever moving them around. And just like that, thanks to these two new heat breaks, we've upgraded our stock Voxelab Aquila to a printer that can safely and consistently print high temperature filaments. Bravo! Give yourself a much-deserved pat on the back. Or, if you're just getting started with this upgrade, you can check the description down below and you can see links to both the heat breaks we installed in this video. And below that is the comments section. And I implore everyone, please leave a question or comment. I want to know what everyone's experience was like with this upgrade. Do you prefer bimetal or titanium? What filaments are you printing that need these high temperatures? I want to know it all. I would love to hear from every one of you. And if you haven't already, please subscribe and you'll get notified when my next video is released. And I thank everyone for all their feedback in advance. And as always, until next time, boys, girls, everybody else, keep on printing.